All right. Okay, let's get started. We're very happy to have Michael Wagner here today. So I was looking through your bio, and wow, you've been doing a lot of things. So 16 years working with robots. You're at NREC now.
Maybe 17 even, I don't know.
Yep. And you're part of your own company.
Yep.
CEO, doing robotics. And there's something interesting here. On here it says that you got a service medal.
Yeah, an Antarctica Service Medal.
How did that happen?
I camped out on the ice for a month with the Nomad Robot, and even if you're not very brave, you still get a medal.
You get a medal.
Yeah.
Well, that's awesome. And you'll be talking about trust and safety issues with robots today?
Yep.
Okay. And we're very glad to have you here. And thank you very much.
Okay, thanks everyone. I appreciate your attention for this next hour. I'll try to make it interesting for you. Yeah, my name's Mike Wagner. I've been at the NREC now since 2006, worked on a number of different projects there, and then before that was at the Field Robotics Center. Red Whitaker hired me back in 1998 or something like that. So I've been involved in lots and lots of different projects. And what I'd like to talk to you about today is sort of the passion that I've had in my work for the past 7-ish years or so, which is how do we take these very advanced, very useful systems that we've been developing here and actually transition them into use in the real world in a safe way. Okay, so up until now, at least certainly when I got started here, a lot of robots were keeping people safe by removing the people from the situation and putting the robot in instead. Okay, but at this point, we're trying to get robots that are working in human environments to do all kinds of important things, and so then safety issues crop up. Okay, so I do want to keep trying to draw distinctions because the word safe is very overloaded in a lot of contexts. Another context that we roboticists use the word safe for is, you know, we have an obstacle avoidance system, or we have a planner that keeps something safe. That is fantastic and obviously required. But what I'm looking at is the reliability of those kinds of capabilities. Okay, so you've built you've designed the algorithm, you've proven something about it maybe. Now you go and implement it on a system. What can we say about that system being able to interact with the world in a safe way? Okay, so as I mentioned, it's always good when technology fails when I'm giving a talk because it just reinforces my point. Yeah, that's interesting. It worked when we were prepping. Anyway, so I got started, as I said, in the Field Robotics Center working on all of these robots, NASA-funded efforts. So there wasn't a whole lot of concern about the safety of, you know, the robots hurting someone, although this is where we were out on the Antarctic plateau, and there's obviously some safety concerns there. But even though we didn't have any real safety concerns here, we obviously cared a lot about these systems operating properly. Okay, we spent a lot of time and effort. There's a lot of cost and expense to take these things out to the Atacama Desert or to Antarctica, and we want them to do their missions, right? And we had fantastic teams of engineers building these systems, but nonetheless, these important bugs kept cropping up in them. Okay, so one great example is the Nomad Robot, which was first built in 1996 and was used pretty heavily through 2000. And during that whole time, it actually had a pretty serious memory leak in the low-level control system that was driving the motors, that was doing the closed-loop control of the motor. So that limited the mission time of the vehicle. And I can tell you, the guy that was on this, that developed the system and tried to debug it, is top-notch. Okay, so it wasn't for a lack of engineering expertise that we had these kind of problems. And then all kinds of systems that I was involved in since then had similar kinds of issues that were really, really hard to fix. And also the other important thing is that they were unpredictable. Okay, we couldn't see them coming. So then in 2006, I went from the Field Robotics Center to the NREC, where I became the software lead for this vehicle, the Gladiator Vehicle, the Gladiator Tactical Vehicle. You can see the tactical parts in the picture here. It's a very serious system that was designed to be used by the US Marines. This was built in the 2006-2007 timeframe. And as software lead, you know, I had a team of again, top-notch developers. We had a lot of resources available to us to do the right right thing to do the testing that we thought we should, but I was still very concerned about the threats posed by these unpredictable problems that cropped up in all these complicated systems that I had built in the past. Okay? And so I started trying to learn more about the processes involved here, and I thought, okay, well, there are gatekeepers that will prevent me from fielding something that is, that has unsafe software, and there must be guidelines out there that I can just, learn about to be able to build safe software. And it turns out there were limits to both of those things, okay? So for example, to the Defense Department's credit, they realized that they have, certainly at that time, they lacked capability to evaluate these complex software-driven systems, okay? Their existing oversight capabilities, their test and evaluation capabilities, were mostly looking at physical aspects of the vehicle, right? So, could it hold up to driving across off-road terrain? Would the mechanical systems fail? But they didn't really have any way to check out these kinds of issues. And similarly, industrial safety standards and whatnot did not really apply to this kind of system because they didn't scale up very well. Okay? So that was 2006 and 2007. In 2008, I started working on this vehicle, the Autonomous Platform Demonstrator, the son of Crusher, you might call it. It's a 9-ton vehicle. And it's capable of driving up to 50 miles an hour. And so we had this challenge here because the Army wanted to use this vehicle as part of a soldier demonstration. They wanted to put it in an operationally relevant area and have soldiers try to use it and see whether it was valuable for the operations that they wanted to conduct. And so to do that, the Army safety people had to come in and evaluate the safety of this system. Okay, so they had to sign off saying, this is okay to have soldiers nearby. Okay, and the way they do that typically is they say, okay, how fast can this vehicle travel? Okay, all right, and we'll take a 2 or 3 second response time, right? Because the response time of a safety sort of driver or a safety person on a big red button is usually a second or 2 at least. And so how far can it travel during that time, and then how long will it take to actually hit the brakes and come to a stop? Well, that puts the soldiers at 50 miles an hour. That puts the soldiers at the next time zone basically, and so that would have made this test completely infeasible. So what we did. The other aspect was this system was completely built at the NREC, right, from skid plate to the highest level software, okay, and so it was a very, it's an advanced system. It was a very aggressive schedule. It was 12 months from preliminary design review to wheels on the ground, okay. So again, traditional sort of safety processes are very, very, I guess, slow, you might say. They're very, very involved and incompatible with a lot of the kinds of projects that, like APD. So I enrolled the help of Professor Phil Koopman from the Electrical and Computer Engineering Department here, and we came together and tried to build a safeguarding system that we could place on top of this vehicle to enforce all these rules that we really cared about, okay? Simple things like speed limiting. Because if we could prove or if we could convince, I'll be careful to use the word prove in front of this group, if we could convince the Army oversight people that we had our ducks in a row in terms of speed limiting, well, now the soldiers could get much closer because that maximum speed effectively goes down significantly. And that's exactly what we did. We had this system which at the time we called the safety monitor. Not a big fan of that word that term anymore, but we called it the safety monitor, and it was responsible for maintaining these kinds of simple rules. So the rest of the system was undergoing a lot of change. It involved potentially hundreds of thousands of lines of code. The safety monitor, though, was a firewalled bit of safety critical code that we could develop at a very high level of rigor, okay, and do all the verification and validation, all the V&V that we wanted to on it, to be able to convince the Army that it would monitor these rules. And of course, if any rule was violated, you hit the brakes, okay, and the big dog comes to a quick stop here. So we had a leash for that big dog, and we were very successful with it, okay? The Army gave us permission to go ahead with our plans using these speed limits as sort of dependable safeguards for the vehicle. this all culminated in around 2010, and our next question was, can we apply some of these same ideas to autonomous vehicles? Okay, because what I just described to you is basic, low-level kind of stuff. Okay, a speed limit. All right, that's not a very complicated rule. Can we use similar architectural tactics to be able to make the same kind of strong claims about autonomous perception and safeguarding? Okay. We face a lot of challenges in doing that, okay? And that's really what a lot of the rest of this talk is about, is what the challenges are, and I think we try to frame the challenges in a very specific way, and then we can apply some interesting testing technologies to them, okay? So again, just to drive the point home that we can't just turn to a standard and build this based on a standard, the sort of granddaddy of all these kind of standards is IEC 61508. If you get into this business, you start rattling off a lot of 5-digit standards, which are really impossible to remember. But this is sort of the high-level one that gets instantiated in a bunch of different ways. The basic idea, which of course I didn't make big enough, is that you have these safety integrity levels. Okay, so you say, all right, I have something that is very, very safety critical. It's the flight controller. It's the avionics for my aircraft. It has to be SIL 4, safety integrity level 4. I have something that maybe is it might, if it fails, it might hurt someone, but it won't kill a plane full of people. That might be SIL 2, safety integrity level 2. Okay. And the way these standards work is that for each of these levels, you have a bunch of different prescriptions that you have to carry out. So in this case, this table here is from SIL 3. What's recommended, what's highly recommended, and what's not recommended for SIL 3. And if you go and you look through these standards, you realize that actually a lot of the things that we do, like reconfiguration and fault diagnosis and fault detection, are things that are ruled out, or not recommended at least, by these kinds of standards. Okay? And so, some of the basic tools we need to make the systems that we want to build are discouraged by this. And you might say, well, they're discouraged because they're new. Okay, they're novel techniques. They haven't had enough time out in the real world to validate. But I think there's something a little bit more central than that. So let's look at a comparison between a typical safety critical software driven system and this kind of a system, which is looking at perception data from a driverless car and trying to make decisions about pedestrians and other cars and sort of keep the car safe and the people around the car safe. Let's take, for example, as a simple traditional system, something like a simple throttle controller, okay? So you have a throttle controller in your car, it looks at the pedal position, and it sets the throttle body based on what you're commanding it, okay? You can take, sort of with deductive inference, you can take what you know about that problem and derive it all the way out to the implementation, okay? You know certain things just by first principles. You know when I take my foot off the pedal, I don't want it to accelerate anymore, right? It should go back to a neutral throttle. All right, these are basic things that then you just deductively put into the requirements and then into the design, and you say, okay, now my job is to make sure that never fails, so I put redundant sensors, redundant decision-making elements, whatever in, but the whole thing is like a very solid chain of deductive inference, okay? Now we compare that to these kinds of systems that use machine learning or probabilistic methods, which of course, as we know, are critical to even getting the job done, okay? We can't build up expert rule sets to say what a pedestrian is. We basically have to train a system because it's too complicated a problem for us to encode explicitly. But now we have these kind of inductive systems, all right, that are based on the idea the world is operating, the world works the way I've trained you that it works, okay? And so you build a model. I don't really know all the details of that model, but there's an implicit assumption in that whole design that as I'm training it with a realistic training set, okay? And this sounds sort of like a typical problem in machine learning where we have to go and validate that training set and whatnot. But I think the mindset is a little bit different when you're talking about safety. Okay? Because when we evaluate these kinds of systems, we're often looking at their performance, their rate of classification or something like that. But when we're looking at safety, we want to look at the worst case performance. We don't want the nominal performance. We want to look at what's the worst that could happen and then safeguard against that. Okay? And that's a different mindset. And this is really critical here because, when we take these kind of systems out into the real world, we run into a lot of unexpected environments, okay? You know, there are so many different combinations of inputs that the world might present you with that, that violate assumptions you didn't even know you were making, okay? And this is the challenge that I think we as roboticists are facing as we're trying to use these systems in safety critical applications, okay? You know, you build your system to try to track a road. Well, there are obvious ways that the road might not be shaped the way you expect it to. Obstacles may not be obstacles may not always come up from the ground the way you expect them to. You know, visual features may not have the coloring that you expect. You know, is this a pedestrian? I don't know. Right? So what we've realized as we started grappling with this challenge is that we should be doing this testing a little bit different, okay? The way that a lot of verification and validation programs are run now is with the following goal, okay? I want to be able to say that my system is X% reliable, right? It's not going to fail, or its mean time to failure is Y, right? I don't want to, and so what happens is we go and we collect a lot of data to try to reinforce that conclusion, okay? We take the driverless car out on the road, we put the drone up in the sky, we deploy the safeguarding equipment and let it run for a long period of time, and we basically say, okay, great, I've gotten to the 100-hour mark and I don't have a failure. I've gotten to a 1,000-hour mark, or I've gotten to a 100,000-mile mark, right, and I haven't seen a failure, okay? The fallacy is that we're not talking, the fallacy is one of failure modes, okay, that we actually care about. That kind of approach is great in a traditional system when you're talking about independent failures that are due to things like wear out, okay? That's where this mindset comes from, okay? You take a car out on the road, you have a new sort of bracket or hinge on it. I'm gonna, you know, expose it to road vibrations for a really long period of time and watch it fail. But as we know, software doesn't care about how many times it's been given an input. It's the range of inputs that we care about, okay? And so this whole idea of collecting these mountains of confirming evidence is, I think, not very productive, okay? Because really, after you've driven over that 100,000 miles or whatever, you just know that over those inputs you haven't seen a problem, okay? So what I would like to do, and this is such a simple idea, but it's crazy that it's not often done this way. What I would like to do is reframe the way V&V works and try to come up with tools and methods that are efficient at finding the problems, just right off the bat, finding the problems, okay? Don't even think about confirming evidence, okay? But think about finding the black swans, okay? Think about this one experiment that disproves your argument that the system is safe. This approach is called modus tollens, and it's based on so much philosophical writing that it just makes you cry. For the past 500 years, right? You know, we're talking about Hume, we're talking about all these guys, which basically says if you have a universal statement like my robot is safe, you're never going to prove it through empirical observations. That's the limit of induction. But you can disprove it with a single observation. And it's that dichotomy that we're trying to take advantage of, okay? It seems so obvious when I explain it, but again, there are basically no safety programs that are run this way, okay? So what do you do, okay? So you have your safety claims you're trying to prove, you actually disprove them, and then you realize that the robot is not safe, okay? So what do we do with that, right? Because we just proved our robot is unsafe. That's not a very useful place to be. That's not the point of this discussion, okay? What we do then is we then iterate, okay, and we improve either the safety argument that we're making, or we improve the system, or we limit the scope of how we're using the system or something. But we basically take this observation and we use it to improve our knowledge of the world. We iterate and then we try again, okay? And this is basically, you know, so Karl Popper wrote a book about scientific method and what it means to be a scientific theory, and his basic idea was it's a useless theory if you can't falsify it, okay? And in fact, the task of science is not coming up with the theories, but refuting the theories. And I'm arguing for exactly the same approach to validation and verification of these kinds of systems. So what do we need to start that? We need an argument that we can falsify. This is another thing that is missing from almost every safety program. We all have requirements, okay? well, we should all have requirements. We learned that in engineering classes. We also learned that those requirements should be testable, but that's not the full story that I'm trying to make here. We need an argument for why it's safe that hangs together, okay? And ideally, that argument should rely on formalisms so that we can mechanically check it, okay? There are a lot of, oh, that looks bad, sorry. There are a lot of examples of how you can do this. Again, if we turn to philosophical sources, we can look at formal argument structures. Actually, in the EU, there are a lot of safety practitioners using what's called goal structuring notation. This guy, Tim Kelly, up here did his thesis at York on this. And the UK Ministry of Defense is, in fact, using goal structuring notation to structure safety cases, assurance cases, safety arguments. And although it's hard to see, I guess I'll go to the next one, because we use the same kind of thing. Basically, a safety case is really just a way to decompose an argument into goals and strategies and claims and eventually evidence, okay? But the idea is that you want to make it explicit, and you don't use natural language, but you actually make it explicit so that you can argue against a safety case in one of two ways. You can argue against the inferences that you're making. So my high-level safety goal isn't fully supported by my lower-level goals, or you can get all the way down to the bottom. And when you have evidence that you're using to support your claims, you can say, well, your evidence is wrong because I have some observation that counteracts it. Okay, so we've used this kind of approach to do runtime monitoring on systems. Runtime monitoring is very similar to what we did on APD, and we come up with a formalized argument for why we believe that monitor is going to help ensure the safety of the system. Okay. Now, again, the point here is that we take this safety case out into the real world, and we start evaluating it. We start trying to falsify it. Okay. And again, here's the different way of thinking about testing. Okay. We're never going to replace the sort of initial field testing, real world testing that you need to do. We as roboticists love doing this. We get to take our systems out to the real world and to exotic places maybe and expose them to real world inputs, and that's really the only way to know whether our system is going to perform. But here's the way I think of it, okay? Again, you have a safety case, your initial safety case, you take it out and you test it until it fails, okay? Simple example here, a system that isn't trained to deal with weather conditions, works fine on the highway until you run into snow, okay? Obvious case, you probably thought of that when you designed it, but just to use it as an example. So we start out with these real world conditions, and we keep going, we keep iterating here until we can test longer and longer without a problem, okay? Now the issue now that we face, okay, after a few rounds of this iteration is that the field testing gets expensive and complicated. Okay, now we have our car, and now we have to go another 1,000,000 miles before we learn something new. So how do you economically deal with that? Well, you typically turn to simulation at that point, which is a natural next step. Okay, because the simulator can produce very realistic looking inputs to your system in a number of different combinations and maybe faster than real time, and so now you can run your next 1,000,000 miles in 1/10 the time that you ran your first 1,000,000 miles, and that's great. But you're never going to simulate the things that you don't have in your model. Okay, and so and that's a fundamental limitation. You're training the system based again on your expectations, but the world may not correspond to what your expectations are, and those are the problems that I'm really worried about. Okay, so we've been researching an approach called robustness testing that we've found to be a very effective way of finding bugs that aren't otherwise uncovered in simulation testing or in real world testing. And so I'd like to tell you a little bit about the way robustness testing works. But actually, before I get to that, one thing that we've been looking at recently is whether or not we can turn to prior work on the psychology of programming to sort of help robustness testing. And it's kind of interesting that if you go and look at that literature, you find out things like this that are very common findings. That programmers are good at debugging once they see an observation of the bug, but if you give them a system and have them analyze it, they're very bad at finding a bug. Okay, this is kind of straightforward for those of us that have been doing a lot of software development, but but it's very powerful, right? The Monday morning quarterback is much better at figuring out what went wrong than doing peer review, design review, code review, static analysis, and trying to predict what might go wrong, okay? So we want to take advantage of that dichotomy too and say, all right, can we think of robustness testing as a way to present developers with failure modes and then have those developers go back and do root cause analysis to improve their system, okay? So basically, you know, if you could send your software through the shaker and come out with all these bugs, some of the bugs may be important, some of the bugs may not be important, but it's basically a vulnerability analysis of your system that you've now automated, and that's we think a pretty powerful way to do that safety case iteration that I was talking about. So, what do I mean by robustness testing? It's actually a general term described by a lot of those standards. We have sort of one specific way of thinking about it, which actually comes from some really simple concepts. The first kind of robustness testing that was developed is now called fuzz testing. Naive fuzz testing. It's basically you send random inputs, purely random inputs to the system that you want to test. And this guy Barton Miller at Wisconsin has been publishing these papers for the past 25 years where he repeatedly runs these surveys over very important software corpuses. I mean, you know, Unix utilities, he's done the same thing with Mac OS repeatedly, and he finds that randomized fuzz testing finds tons of crash problems, okay? He can get systems to fail in really interesting ways and completely unexpected ways by just, you know, catting dev random into the utility, okay? And it's sad how he keeps basically replicating his results. You know, as an academic field, if we are concerned about replication, this guy's got it down. Okay. Now there are some challenges here with fuzz testing. The challenge is, how do we know how the system under test should behave when we give it random inputs, okay? That's called the test oracle problem. And the solution to the test oracle problem for fuzz testing is we just look for really simple problems like crashes, okay? So we say if you core dump, that's a problem. If you kernel panic, that's definitely a problem. And that's our definition of failure. And so we're actually letting, our failure detector is actually quite coarse and bad. We're letting problems pass through without even realizing it. But the fact that this still finds problems all the time means there's a ton of low-hanging fruit, okay? Now the reason why we do this is because it's completely automated. That's the obvious one that everyone thinks of, is that you can run this test in the background, there's absolutely no test planning required, and it pops out bugs, okay? It's shaking these bugs out just like I was describing. The other benefit of this with randomness is that there's no bias. Okay? Again, the simulation example I was saying, it presents your system with biased inputs. If I had some, you know, canonical feature space that I defined as, you know, or some canonical input space for my system, when I look at the inputs I generate in real world testing, in simulation, they're probably going to be very clustered. All right? But if you look at what the input space could support, you know, there are all these regions that are left completely unexplored. And this is an unbiased way to kind of, you know, sample some of those regions. Not completely sample, right? You can never prove anything with this kind of testing because the input space is so huge. So Phil's group in the 90s ran a project called Ballista, which did the same kind of thing with POSIX APIs in operating systems. And he sort of went one step beyond naive fuzz testing and used what you might call a dictionary attack. Okay, so what his group realizes, okay, we want to test all these POSIX APIs and these different operating systems. There are really only a few different data types as opposed to like the larger number of functions. So let's come up with values or dictionaries of potential interesting values for each data type, okay? So Ballista looks at this write function, it tries to test it. It builds a one-line program that passes parameters in here and tries to get it to crash, okay? Again, it's looking for simple problems because the test oracle problem is still there. So we only know that we failed if it kernel panics or something or freezes. We don't know anything about what write does, but we know that it takes an int, a pointer, and the size type. And so basically Ballista would select from these randomly, come up with a function called run it, or compile it and run it, and see what happened. Okay? And it turns out lots of interesting things happened. Okay? You can see this is old because of the versions of the operating systems, but one of his students is looking at, you know, doing the same kind of survey for Android today. The idea is that you can pop out he called them catastrophic failures. You can think of them as kernel panics. You need to, power cycle the system to regain control. Okay, and this was interesting because at the time, some very important customers were thinking about using operating systems like QNX. Okay, this is QNX, that's the industrial OS, tens of millions of dollars of development, fielded widely. Okay, they were thinking of using QNX, and they really had to take a look at the weaknesses in this API. Some really interesting things popped out of this work that I won't go in here, but I can forward you to about sort of where all these bugs exist. They tended to be localized in the API, and so you could come up with hypotheses about why that was. So maybe memory management is more complicated than file I/O, or maybe the team in charge of developing the memory management section was newer and hadn't been trained as well or something. Though you do have these sort of areas, these bug farms, they call them, that do pop up in different regions when you test different versions, but they never go away, which is, I guess, good for my business, but bad for the rest of the world. As I said, there are some trade-offs here in how you do test generation. I think the main benefit of this is that what I'm talking about is compared to a very manual process that we follow today. If you look at unit testing, you're often generating the test oracle by hand. You're giving a unit test inputs and you're saying how it should respond. That's a very manually intensive process, and we'd like to push that up towards the random side while still being able to find bugs. Okay, and so by doing that, we increase scalability. We decrease the bug search bias, which is great because we find, in security terms, you find 0 days if you're not testing the kinds of things that you would normally try. But again, our test oracle becomes it lets failures pass because we don't know how it should behave in random inputs. So I mentioned that the Defense Department, to their credit, acknowledged that they didn't have a lot of the software testing capability for these complex systems. We had a lot of conversations with them about that, and in 2011 started a project called ASTAA, Automated Stress Testing for Autonomy Architectures, that applied ballista-like test generation along with what's called runtime verification to stress test software in charge of autonomous vehicles. So the government was very interested in how do you test these autonomous systems, and they have a lot of different approaches that they're funding, but this one is really how do we look at robustness testing in the context of these kinds of systems. We can test these systems in a number of different ways. We can test full up vehicles on blocks if you wanted, but we can also test complete software systems in simulation. We can test individual software modules or even code units. And the idea is that we can start by doing essentially what Ballista does and looking at the interface definition and coming up with inputs just based on that interface definition, okay? We can just generate random, if you have a ROS message that your system is using and it's an array of floats, we'll fill up that array with random floats and see what happens, okay? We call that injection. That's like the simplest form of testing. We can actually go all the way down to a pretty powerful form of testing called interception. The security world would call this mutational fuzzing. The idea of interception is that you have sort of a man-in-the-middle kind of attack, you might say, where you have one component speaking to the system you're trying to test, and we go in and we probabilistically modify that real-world data to replace it with that dictionary of interesting values to see what happens. So this is really interesting because this allows you to sort of penetrate the system under test more because you're giving it somewhat realistic inputs, right? So we're doing dynamic analysis. That's what we're talking about here. So if we can't run a line of code, we're not going to be able to tell you whether that line of code could pose a problem to your system, okay? So we have to be able to run it. And if we're doing injection and we're giving random inputs to a fairly robust system, it's just going to reject them, all right? But interception allows us to get further into the existing system to find bugs. We've also done it on very low-level hardware networks like CAN buses. I'd be happy to talk at more length about that later if you'd like. The other important component is runtime verification. I've talked to you quite a bit about all this stuff, which is how we generate tests. But runtime verification is quite important because we're not just looking at software crashes anymore, okay? We're trying to find safety problems in these autonomous systems. And so how do we set up a test oracle for safety, okay? What we do is we look at, if they exist, safety requirements for that system. And the reason why safety requirements are such great test oracles, okay, is that they should hold no matter what input you give it. Okay, think back to APD. Okay, APD, I said, had this really complicated mobility control system, but we had a safety monitor that maintained speed limits. So the safety monitor invariant was, no matter what commands, what speed commands you sent the underlying system, you should shut down if you get an out-of-bounds speed command, okay? All right, so that's a great test invariant, or that's a great test oracle, I should say. So we know when tests fail in much more nuanced ways. So what ASTAA basically does is it's reading signals from the system under test and evaluating these terms, or these MTL terms that form our invariants. So we use temporal logic to write our invariants because we need to mechanically evaluate them during runtime. We can't just deal with natural language, English requirements, which is actually what we typically start with. It's interesting, having done this for a number of different groups, different clients, that we actually learn a lot trying to write the temporal logic form of an English language requirement, because there's ambiguity in the original requirement as it's written. Any of you who've done formal methods have probably run into this all the time, and we run into it as well. We use metric temporal logic because in our systems we care a lot about time windows and response times. So we need to have metric time, not just a response or a request gets a response eventually. So we have an MTL engine that's running within ASTAA that's evaluating all the different invariants that we want during test time. And we've used this technique on over 20 different autonomous systems so far. Several of them were developed at CMU, but our contract specifically called us to do more than that. We got involved with the Army's Autonomous Mobility Applique System, which is their autonomous truck convoy. There you go. You can see it's autonomous because we have the video of the steering wheel with no hands. And so we've been working with them for the past couple years. We've also run tests on software in control of Herb. Some interesting results there that got fixed, which is good. We've tested UAV software. We've gotten involved with the chimp robot at NREC, and we've also done a lot of testing of open source systems. And the kinds of problems that we find are really quite varied. I'd like to spend a little bit of time explaining them to you, because this is really where the value of the approach is, of robustness testing. So we do get a lot of problems that you might expect, like if your interface is complicated, and it's going to have a lot of implicit assumptions that don't get enforced by the software that's receiving messages through that interface. Okay? The most basic example of that is floating point variables. Floating point has out of bounds values, not a numbers, infinities, etc., and nobody handles those. Just nobody. Like, I don't. I actually used this tool to test code that I wrote, and I had the same kind of bug. In fact, we used it to test code that we wrote, and we found, like, on the project, on the ASTAA project, we had the same kind of bug. So I'm not claiming that I'm like an expert. We need the tool, right? So you find a lot of things like that. NANs, NANs are difficult because, if you compare anything to NAN, the result is always false, and that's counterintuitive. You have to do an is NAN check. But there are lots of other really interesting things we find. Time, a lot of your systems that you're testing that are control systems are assuming monotonically increasing time. Doesn't have to be that way, okay? And in fact, I've worked on some projects that have run into a problem like that in the field that we later went in and found was because of a time handling vulnerability. Array indexing is a really interesting one to me because this is kind of a variant of your classic buffer overflow problem, but it's writ large in robotics because we're doing map updates all the time. We're doing like partial map updates, and again, so many implicit assumptions in what those updates, in the structure of those updates and the implied bounds of those updates. There are so many ways you can just miss something and have a vulnerability. And finally, there's a lot of dynamic state, and by that I mean like lists of trajectory commands and things like that are easy to get wrong in different ways. there's one example that I like to use in the context of perception systems. Perception systems are very difficult to test because they're very high dimensional, and we have the test oracle problem. So what we do is we like to set up data that simplifies the test oracle problem. And in this case right here, my timing is really bad on this. On this video, we found a bug. I'll just say we found a bug where we can get the system to crush this poor human. The idea was that that this robot arm model is never supposed to collide with things in the room, right? And so you might say, well, how do you set up a test oracle for this? You need to replicate the safeguarding system to know whether it's safe or not. Well, in our tests we actually used a fixed base arm, okay, and we put the person, the fake person, of course, right up to the fixed base arm, and then we tested just through the arm joint feedback interface, okay? So we knew, as an invariant, no matter what happened, the system should always try to stop the arm, okay? But we found a vulnerability where if we sent an invalid joint angle in, the robot arm, the robot model actually disappears, which is why then there's no intersection found. And so you can trace this down to a very simple, like, floating point bug, okay? Which once we found out about it, it was very easy to fix, right? But then, you know, as we thought about this a little bit more, gosh, well, how do we guard against other similar kinds of bugs? And that dramatically improved the architecture of this system, okay? So there are lots of interesting case studies that we can go into. I can talk all day about them. We did some surveys of open source software, like I mentioned. Eigen was one really interesting example for us. We tested Eigen function calls to try to find ways to get them to fail. And again, we're randomly here. Again, this is a little bit different than fuzz testing, like an IT kind of, you know, web server kind of system. This is auto-generating matrices and sending them to a function and seeing what the function does. Okay, so we have this SVD function that actually in the documentation even thinks about nans and infinities, which I thought was really cool that they thought about that. And they said, okay, even if you pass them in there, the function's guaranteed to terminate in a reasonable amount of time. Okay, that's good, right? That's what you want it to do. Well, it doesn't work that way. We were randomly generating these things, and we got it to essentially, you know, get caught in an infinite loop and never return. Well, never return. I guess we still don't really know if it never returned. It's not reasonable. Let's just say it's not reasonable amount of time. And it's interesting how simple the input is here, right? This is a 3x3 matrix with one nan. Okay, so that's kind of cool and kind of scary. We also are very good at tripping asserts that you didn't know were trippable anymore. This one is interesting. When you pass this matrix to this function, it trips this internal bug. Again, black box testing, although we can go in and figure out the root cause of that by looking at the code later, but actually running the tests doesn't require any code analysis. And the interesting thing here was that we reported this bug, and the last one as well, to the developers, and they went back and they patched it, okay? But they didn't really patch it. They patched it for the test case that we came up with, but then we kept testing and we found more. And in fact, we found a 2x2 matrix, which was really exciting, you know. 4 values into, you know, and what sort of Kalman filter or something would ever produce a negative infinity, right? We've never seen that problem anywhere.
How many tests did you judge this?
How many tests did we use? So I would guess probably thousands, not that many. Not that many. I can get the actual answer for you because we have these logs. But typically, a lot of the stuff right now, so we're very early in this arms race, I guess you might call it, and this stuff is really good at finding bugs. We had this vehicle at NREC called RecBot. It was a John Deere e-Gator. Okay, and it was the first system that we tested, and we just basically tested it because we wanted to validate that our message sending and reception was working properly, right? We thought, okay, it takes a speed and a curvature, 2 fields, so we're not going to be able to find any problems, but we just want to see that it's working. 4 minutes after testing it, we found a speed limit violation because the speed and the curvature commands are floating point fields, and it didn't handle NaN. And that was cool because it was up on blocks, so we got to see wheels actually go kind of crazy. But it is an arms race, right? Because the world will start to run this kind of testing on these systems, and then we got to get trickier, which is why I'm talking to you guys, because I had a couple good ideas to get all this stuff started. We need a lot of good ideas to keep this kind of testing going.
So how much domain knowledge goes into generating those cases? Like for example, in
Yeah.
this case, was there somebody who had knowledge about what eigen does as a black box?
Nope. Nope. It was just it took a matrix. It took an arbitrary sized matrix. We basically, you can think of it as we need the IDL, and that's all that we need. And the fact that we don't want it to crash, right? So we need the test oracle as well. Yeah.
So in the first example, how sensitive do you think it is to that e to the 308?
Oh yeah. Oh great. Okay, I have an answer to that. Yeah.
It's only testing thousands, and it has to be exactly that. Okay.
Yep. So I have a slide on it. That's actually perfect. Thank you, Reed. So again, going back to programmer psychology, which I really want to get more involved in. I don't know anything about programmer psychology, but I want to learn more about it, because as I learn more about it, I start finding all these interesting nuggets that people have run into. Like for instance, that people are bad at debugging, and they make a modification to try to debug something, which leads to more problems. Okay, again, we've seen this happen, okay? But it's interesting that people are thinking very deeply about this, okay? That was exactly the case that we just saw, right? They made a modification and it either caused new bugs or it didn't really solve the bug. So what we've worked on after that was fault diagnosis, and this is what's getting to the answer to your question, Reed. So what we have actually, I'll just skip right to this slide. What we have is an automated system for finding specific instances of inputs that cause a problem. All right? And that's useful because in a lot of cases you can rerun those inputs and still find the problem. But what we really want to learn is what you brought up, is what is it about that matrix that's actually causing the bug. So we have a three-step process, and this was all developed with Paul Vernazza on the ASTAA project over the past year. I have an interesting paper I can give to you if you're interested in learning more. So we have an automated way of doing robustness testing and finding bugs. Then we use delta debugging to simplify which messages are actually involved. So if you think of here, we have a problem that we found. It involves sending a test case of 1,000 messages. Delta debugging will say, all right, it's these 3 messages that are the important ones. And then what Paul's algorithm does is it tries to fit a product set of field values to so what it does is it queries the system under test to try to generalize that one instance that it has, to learn what it is about those fields that's important, okay? So, and here's an interesting example, all right? We tested an autonomous system. We found a bug where so the system is supposed to emergency brake whenever the reported speed is above a value, okay? Again, we keep running into these kinds of issues, but they're important. And it was in a particular mode, okay? And so we found the bug, and it was maybe 1,000 inputs. We ran delta debugging, and it came up with 3 messages, right? M0, M1, and M2. And then we ran it through this hierarchical product set learning, and it identified that this was the product set that actually caused the violation. So you have these first 2 messages that actually are getting the system into a state where the speed limit needs to be enforced. So that was interesting that we learned, Hipsel actually learned a little bit about the protocol of the system under test. But then the interesting bit here is that if the actual speed is a large negative value, then we have a problem, okay? Now, you may ask what it is about negative E that is so important. There are a lot of important things about negative E. The only important thing here is that it's in our dictionary attack, right? So we thought that would be a cool thing to try, okay? Now, again, this is black box testing. All we know is that we have a particular IDL that we can send data through, and that we have the speed limit invariant. But when you look at that, you think, gosh, I wonder if they forgot an absolute value, because there are no positive speeds in that product set. And then we went and looked at the code, and we actually found a line of code that was, if the speed is greater than the speed limit, then emergency brake. And of course, we need fabs around the speed, right? And we caught that here. So this generalization is we think really valuable in the process of taking the results that we found and using that to improve the software. Okay, and this is one of the best examples. But HIPSL is something that we use as part of our everyday course now. It's very efficient. It's an active learning method, and we take advantage of the fact that we're running in software, so we can take a unit and we can send a lot of inputs to it. So we basically go from a random round to find the problem to a directed round to generalize the problem. The other great thing is we had looked at other passive methods for it, doing like decision tree learning to try to learn rules, but there are a lot of parameters that you have to tune. HIPSL doesn't have those parameters, but the biggest limitation is that it's trying to fit a product set to the bug, which is, there's no reason why the bug has to behave like that, right? So you can imagine a bug where your system fails if field X equals field Y, and we wouldn't be able we wouldn't be able to generalize that bug, okay? But it's great, again, sort of like fuzz testing finds all these problems right off the bat. This kind of learning provides a lot of value right off the bat. So one of the reasons why I was really excited about talking to you guys today is that I think that this is a critical subject for our industry. I have a group of probably now about 10 people involved in this kind of research at the NREC. We have ongoing work this year, and we have a lot of interesting things that we're getting involved with now as well. You know, at the outset, it was mentioned I'm trying to commercialize some of this capability too. There's a lot of really exciting things we can do with this, but there's a lot of really important fundamental research that I would like to work on with some of you. The first most obvious one is picking up on what I just said, is that I think this fault diagnosis is really, really critical. Because you can imagine that fault diagnosis, if you know what the general problem is, you could even set up a wrapper, right, for your system. If you have a third-party library, you can't modify the library, or maybe you have a piece of firmware running on a chip that you have no access to, but you can guard it in a certain way, right? Then knowing what the general failure rules are is very valuable, because you could maybe reject those inputs just out of hand, right? So we need to do fault diagnosis with more complicated models that we try to fit to the data. There is a proposal that I put in with Drew Bagnell, Jeff Schneider, and Phil, that was looking at trying to learn correlations between the system under test itself and the bugs that we find in robustness testing. So again, if you have this really effective way of finding bugs, you're going to get a lot of data, and then are there aspects of that interface definition that you can look at and say, I think that this bug is going to be in there, and then use that to try to motivate more testing? Again, I'm thinking the next step of the arms race, once the simple testing stops yielding good results, we need to get better and better at it. And I think that we've already amassed a pretty good database of results that we can apply to this. DARPA is looking at doing this in the large on the MUSE program, and so that would be something we're very interested in getting involved in. I mentioned wrappers. I think really this is sort of a simple first idea for what we could do. The DARPA hard idea is, right, to fix the problem. That's quite a challenge, but you know, if we know again what the generalized problem is, we can start to suggest fixes back to the developer. And really, when you're talking about testing, the value of the test is not the test result, but the improvement that you make. Okay, so and finally, I think there's a lot of value in looking at the field of programmer psychology. And using that to sort of come up with heuristics for how we keep finding these kinds of problems. Again, maybe correlating them back to looking at an interface and saying, gosh, there's probably an implied assumption here just based on the structure of the data, and can I exploit that, right? I think those are all things that me and my team are very interested in working with you guys on. So, all right, so that's it. If you have any questions, I'd be happy to take them. Thank you for your attention. I'll drink my chocolate milk now while you ask questions.
So you motivated this by showing, you know, the Velodyne type inputs and vision inputs. You're talking about dimensionality, million dimensions, not thousands of inputs.
Right.
And the probability that you will get an input that actually corresponds. So most of the times, if you generate random inputs, the system's going to do the right thing. It's going to do nothing.
Right. It's going to reject them.
It's going to reject them. Mm-hmm. it's the case.
Yeah.
I disagree, but it was.
But the point is, it's those, you know, the case where you get the yak in the middle of the road and
Oh,
you
yeah.
happen to get a input that looks like that.
Yeah, that's right.
How are you going to do that?
I'm not claiming to auto-generate the yak.
No, but through random testing, you know, with millions of inputs, how are you going to generate things that, I mean, generating, you know, matrices for you know,
Eigen, yeah.
is not a problem, but in the robotics and getting robotics out in the world, you really want to generate things that have some semblance to reality.
Right. So, so there are some sort of black art that's still involved here, right? And so the great example I think is that missing robot model. We call it the missing robot test because we use that as an analogy in a lot of cases. You can partially structure the data and test through some of the interfaces to come up with fundamental problems in the system. And so you're still going to leave things maybe undiscovered, right? Like the yak. Again, we're not going to find the yak, but you're going to find architectural weaknesses where if the scans aren't formed the way I expect them to, I'm going to stumble upon some aspect of that and then back solve from it to figure out what the problem actually is. Okay, so like another example that is apropos here is we tested a system that was doing ransack model fitting based on some sensor data that it was getting about the world ahead. Sorry to have to be hand wavy, but when you're a tester, you can only go so far into specifics of other people's systems. And there was a flaw where that ransack loop would never stop iterating if the structure of the points wasn't what you would see in normal operation. Okay, and so those, I mean, really the right way of saying it is not that we're going to come up with a scenario, but those we're going to stumble upon those implicit structures that we're expecting to see, right? Now, the important part of this right now is the human engineering that takes that test case and figures out, you know, where the problem really lies, but getting the example allows us to leverage the developer's creativity in a smart way to be able to go back and figure out the root cause. And also, I do kind of disagree that random inputs to these kind of systems don't come across problems, because they actually have in practice. And now the next question is, what's a fault model for that? And well, if it's a safety critical system, you don't care so much about what the fault model is. Your interface allows that data to come in, so it's your responsibility to deal with it properly. But we have run into a bunch of systems where one NaN in your map screws everything up. And you want to know about those too. Yeah.
Two questions. First, don't get me wrong, I think safety is important, but is the problem facing us right now?
Safety is number one. Safety is problem one.
So is the problem facing us that the robots we build are unsafe, or is it our expectations are unrealistic? There's no way you could possibly.
I don't see this as a problem. Okay, I really don't. I see that you know, the people here have over the past 30 years figured out ways to solve all these problems. Okay, and now that we know what we need to do, we need to sort of backfill and know how to do it in a dependable way. That's really the challenge. But the problem is that all the people that are doing dependability, they're like way back here again, looking at like, you know, throttle control systems and simpler kind of embedded systems, and so all the techniques they use just don't scale up. So I don't think that there's any reason why we can't solve these problems. It just takes a different approach. And one reason why I like this black swan testing idea is that it allows you to be really creative about the tests. Okay, and as we do that, that's going to create a lot of sort of institutional knowledge about the failure modes that we run into all the time. So, like for example, we know now after testing, you know, lots and lots of systems, always test through the pose interface, right? Just always do it, because there's always a problem in there somewhere. Okay, and this is like, you know, if you talk to a bunch of aircraft wing manufacturers, right? They know what kinds of problems to just look out for, and as a result, aircraft are really, really safe. So we're just trying to accelerate that mature, you know, line of maturity here. But I don't think there's anything fundamental. You just have to work hard.
Look at the title of your talk, Developing Trust in Autonomous Systems.
Mm-hmm.
The work you presented is in finding more bugs. But you also have this great quote in there, which is you can never, I forget exactly what it is.
Yeah.
Wrong. Am I ever going to trust a system?
So there are
Formally verified.
There are, I hope that, so at some point, this gets back to what you're saying about safety being important but not the only thing, right? It's an economic decision, okay? So like if we're talking about self-driving cars, right, we have so many deaths right now, can we get to the point where we've run enough tests, we've tried enough things to say, all right, I'm pretty confident it's going to be less than that. Fundamentally, there's no domain where you ever really prove these things when you're out in the real world. So you never really have this termination condition that you can satisfy. There are a lot of people, again, in the EU, a lot of this work is going on in the EU that are looking at concepts of as low as reasonably practicable risks. So you basically formalize that economic trade-off and say, well, look, I can't do anything more. I can't spend anything more to build the system. I've done everything that I can, and so that's the basis of my argument.
That leads me to the second question, which
Yeah.
is, if we have these engineering constraints, it seems like you argue against bias in your test case, but it seems like bias would be a good way to get efficiency back in your test case if you could generate samples focused on what you expect to see in the world.
Yeah, sure.
More than just running the car.
Yeah. So like, again, there are a lot of comparisons to security, and that would be, the scripts of known attacks that you would want to rerun on the system. Absolutely, a good idea. You need to do that too. Yep. Yeah.
Could you invert error cascades where I imagine that you've got some downstream process, a low-level control, and you find that it takes a negative number and that causes it to fail? Or let's say it doesn't take one of those edge cases, but it takes like a normal set of data that
Sure.
fails. Would you be able to identify that some upstream process caused that, and then go back and invert that and try to create the inputs that...
See, I'm really glad I'm talking to this group, okay, because that's actually something that we've proposed to do. We call it invariant chaining. And the idea, and if you have a black box, then you don't know really what's going on inside it. But if you have a little bit of internal information and you know how these units interact, then yeah, you basically have a call graph, right? And you're trying to chain, you've randomly found a case that causes a problem, and then you're trying to say whether that's externally activatable. I think that's a big deal, because from the developer of the code, you might say, well, I find a bug, I want to fix it if I have the resources, but how do I allocate those resources? I probably want to fix the ones that are externally activatable first. And this kind of chaining is one way of determining that. We have not really, and we've done it anecdotally, but we haven't done it in the large yet, and we really want to. So great idea. Yeah.
At the end, you said that you were planning to develop heuristics to improve the testing, right? Based on programmer psychology.
Oh yeah, right,
but the main strength of the system is randomness, right?
Yeah.
The minute you take heuristics, isn't that affecting the randomness? And how do you prevent your assumptions to get into the heuristics itself?
Yeah. So that's an absolutely good point. Again, we're talking about testing here, okay? So multiple kinds of testing are all going to be useful because we're never going to fully cover that input space. So absolutely, you hit on a really good point. But so you would want to do random testing. You would want to do some interception, right? Because again, the interception approach biases the data towards realistic data, right? But maybe sort of fewer steps of distance between normal data and your test inputs is good for some reason. So yeah, there is a bit of a tester's black art that still goes into this, and we haven't done anything with programmer psychology models, but it might be that those models are based on the same assumptions that we are already using. So our assumptions are all based on the IDL, the interface definition language, and so maybe if there's some model about how programmers set up interfaces between blocks of code, it's sort of the same bias anyway, so it's maybe just a better it would result in a better dictionary attack. Yeah.
To build on what I said a little bit ago, would you also be able to take that and create more robust simulations where I've seen presentations where people are trying to make like ultra realistic simulations.
Yeah.
And they think about it like, oh, what if I need to create some kind of wind cross current or something? But by iterating millions of times, you can figure out inputs that cause that kind of failure that they may not have even dreamed of. You create a dictionary of things that like these need to go into robot simulators.
Yeah, Yeah, so, but it's definitely like the backward direction instead of the forward direction, right? Because we don't know, like again, if you're randomly sampling the input space, you don't know whether any of those things is going to actually be recreatable in the real world or not. But humans are really good at figuring out tricky ways that might happen, right? So if you have that example, you can say, oh yeah, well that would occur if GPS drops out at night or something like that, right? You know, when the spacing between the trucks is too small or something like that. You can find that case and then bookmark it essentially in future tests. Yeah. Mm-hmm. Although it is interesting because when a lot of people, not a lot of people, I say that too often, when some people hear robustness testing or stress testing, they're thinking about scenario generation instead of input generation. And I think that's the wrong approach, right? So the simulator people are saying, well, we're finding bugs because we're simulating wind, right? So that's going to give you real wind inputs, okay? My approach is, well, we don't know really where the bugs are, so let's just randomly sample and see what pops out. So we like testing inside a simulator because it lets us do that interception that I was talking to you about, but we actually don't care that much about the fidelity of it. From our point of view, we care about the fidelity only as far as that it executes lines of code, right? So if you have a really low fidelity simulator, I don't know, it's like a straight road highway simulator. You're never going to simulate the intersection handling behavior or something.
Well, I would say it's fidelity in the model the schools go. But if you think you've got a really high fidelity model, then in real life, it's never really going to do exactly what you're describing.
Yeah.
So that's not really a rebuttal.
Yeah.
I'm agreeing with you.
Yeah. No, it took me a second to process, but yeah, that's right. Any other questions? Out of time. Okay. Well, I'll be here if you have questions. Thanks, everyone. Thank you. Thanks for coming.
Yeah, great talk.
Thanks.
So, yeah, can you take that?